Thank you, Alec, for your introduction, and thank you for your invitation also, and thanks for all the participants to assist to this talk. So, as you can see in my title here, we'll speak about two parts. So, in the first part, I will try to talk about hyperbolicity notions in complex geometry, like perspectives and how to view hyperbolicity in a complex setting, and the different notions that can be defined this way. And then I will try to talk about holomorphic deformations, which is my main interest in this subject for my PhD thesis. So, uh, oh, this is not working. Sorry, I don't know why I have some. It was working like a minute ago. Okay. So first, I will start with my first part about hyperbolicity notions, and so the motivation behind defining hyperbolicity in so we can define it in two ways. Let's say from a geometric point of view and a differential point of view. Let's start with the geometric point of view. It dates back to the so to the theorem of Liouville about holomorphic functions in C. So one way to see, because like let's say that we have a model of hyperbolic spaces and one can say, okay, they're like the half plane or in the ball model. So let's take out like the ball as a model. So we will try from like from properties of the ball and try to translate them into and try to generalize them in order to introduce hyperbolicity notions. So, for instance, one properties of the ball is that it's bounded. So, one way to introduce hyperbolicity is using boundedness properties, and we know that in the complex setting, that entire functions on C or in general in several variables on CK, if the holomorphic function is bounded, so it's constant, and this dates back to Liouville, and there is this. Other way to to say we can view it from a metric point of view also. We know that the ball has this special metric, which is the Poincaré metric, which is one of the models of like metrics with a negative curvature, which is, by the way, here we have this normalization, real normalization to have -1 curvature on the unit disk. And we have also this famous theorem in complex analysis due to Schwarz and Pick, which says the following, that if I have a homomorphic map from the disk, unit disk to itself, then we have the following inequality. So in particular, what does it say? That in particular, any holomorphic map on the unit disk is actually distance decreasing. So, for instance, if we take W, the limit as W goes to Z, so we get that the derivative of f in the point z divided by 1 minus the modulus of f of z squared is less or equal than 1 over the same quantity, but in z, not in f of z. So basically, what does it mean? It means that uh, the pullback of the Poincaré metric is less or equal than the Poincaré metric itself, meaning that any homomorphic map is actually distance decreasing. So, and maybe the first one that has introduced some hyperbolicity notion in the complex setting was Kobayashi, by using this theorem and try to generalize this to any complex space. And so. one can so Kobayashi did the construction this way. So he defines the Kobayashi pseudo distance a priori through what we call a chain. So we fix a complex manifold, which is a priori non compact or not compact. It's not important at this point. Take any complex manifold and take 2 points in this complex manifold. So what we call a chain connecting 2 points P and Q is a collection of holomorphic maps Fi and points Pi following such a path. So the first holomorphic map from the disk, so it takes the origin to the first point P, and then we have another point P0 on the disk, which goes to the image of the F1 and etc. until connecting and drawing a path connecting points through holomorphic maps from the disk to X inside the manifold X, and as I will take as a notation as CPQ as the set of all chains connecting PQ, and so a natural way to define a priori distance here would be using these chains and define a metric on X using the Poincaré metric on the disk. So the following defines a pseudo distance actually, so it's not it's actually degenerate. As for instance, if one can take, so this one is what we call the Kobayashi pseudo distance. So as an example, for instance, if you try to compute the pseudo distance on Cn, or C is actually identically 0, because if you take any two paths, so one can connect them by a straight line, and you have a parameter epsilon to control and take it to 0, so you get the distance between any 2 points are actually 0. And as one may expect, is that the Kobayashi pseudo distance on the unit disk itself is actually the Poincaré pseudo distance. Okay, so this leads to the following definition. So actually, what we call Kobayashi hyperbolic, or is actually a manifold, in which case that the Kobayashi pseudo distance is a genuine metric or a distance. Okay, and so one property is actually that can throughout this property one can construct examples. So we know that if we take a complex manifold and we take some covering of that manifold, so this Kobayashi hyperbolicity property is hereditary. So it's if the manifold is Kobayashi hyperbolic, the universal cover is the covering, sorry, is Kobayashi hyperbolic, and vice versa. And I will use this maybe to discuss some further examples. So maybe from this two examples where we have the Kobayashi pseudo distances computed, so we can see that actually Cn is not Kobayashi hyperbolic, and one can use this to show it's not difficult to see that actually if a manifold is Kobayashi hyperbolic, we have the following property in terms of holomorphic maps from Ck to X are actually all constant. So in particular also for K equal to 1, which is a very interesting case that we will see later. Okay, so this you can be proved just using the fact that the Kobayashi pseudo distance on Ck is identically 0. Okay, and the fact that, as I said before, that holomorphic maps to Kobayashi hyperbolic manifolds are actually distance decreasing. Okay. So first example that so since the Kobayashi pseudo distance on the unit disk is actually the Poincaré pseudo distance, so it's a metric. So the unit disk is Kobayashi hyperbolic, or else like what would be? And thanks to this property that I mentioned now, we have that every bounded domain in C is actually Kobayashi hyperbolic. And by the property of the universal cover that I just mentioned for the coverings, so in the compact surfaces, Riemann surfaces like complex curves of the complex curves, we have this uniformization theorem. So it's so to study the Kobayashi hyperbolicity of the Riemann surface, the compact Riemann surface goes to the study of the Kobayashi hyperbolicity of the universal cover. And Cn, sorry, C is obviously not Kobayashi hyperbolic. As we said, the pseudo distance is identically zero. And the projective space is also not Kobayashi hyperbolic, since we can find this, for instance, the natural inclusions that are holomorphic, which contradicts this theorem that I just mentioned up here. So the only case that we are left with are actually the ones covered with the unit disk. So Kobayashi hyperbolic compact Riemann surfaces are actually those of genus greater or equal than 2. And as I mentioned, so as I just mentioned, in general, in higher dimensions, Cn, of course, is not Kobayashi hyperbolic, and also complex tori, since their universal cover is Cn. Sorry. So one can say, okay, we have this one-way implication that Kobayashi hyperbolic manifold, in a Kobayashi hyperbolic manifold, all holomorphic maps from some Ck are constant. So in complex, in particular, the complex lines are constant. So what about the converse? Okay, so this first remark that we have seen that in general it holds true, as I just mentioned, this is the theorem by Kobayashi. But the other way doesn't work in general. This Kobayashi mentions in his book an example by Eisenman and Taylor, which is the following. Okay, so one can show by hand that actually using projections either to the first or the second coordinate of this manifold and try to compose with the functions that takes z and w to the coordinates z and zw, and show by hand that one can construct actually a path with using some parameter epsilon, and prove that the distance between 2 points in this x actually can be 0, even though the 2 points are different. So in general, it doesn't work, but in a quite interesting article of Brody, he showed that actually the converse holds true in the compact case. Okay, so he shows that actually Kobayashi hyperbolicity is equivalent to not having complex lines. So one can also find in literature, for instance, this property of not having complex lines in X called Brody hyperbolicity. Okay, but I will just not use this terminology here, and I will. Like from now on, I will try to speak in the compact case, in the compact setting. So for me, Kobayashi hyperbolicity, you can forget about the pseudo distance thing. From now on, we can see this as the non-existence of complex lines in X. Okay. So this approach, so it's in terms of curves. Okay, so in the compact case for the Kobayashi hyperbolicity, it can be expressed in terms of curves. One can ask about generalizing this to taking out holomorphic maps like from other dimensions. So this can be, of course, generalized, and for this, so we need an immersion metric on a compact manifold X, and I will define this in the degree in dimension n minus one. You will see why in an instant, but one can generalize this approach in any dimension k greater or equal than 2. K is equal to 1 is Kobayashi hyperbolicity in the compact case. Okay, so Cn minus 1 has this standard Euclidean metric that I will denote by beta, and so if I take so if I use the yeah, and maybe also, sorry, I forgot to mention that. Okay, that if I have a Hermitian metric on X, since the map that I define F, I suppose it to be non-degenerate, its pullback, it defines some kind of degenerate metric on Cn minus 1, which means that it's positive outside of a subset of Cn, an analytic subset. So it's of codimension greater or equal than 2. Okay. So and I don't want to go through technicalities, but using like the Hodge star induced by this the pullback of omega, one can define an area measure on spheres. And the thing here that what one would expect is that we can take out all the holomorphic non-constant holomorphic maps from Cn minus 1 to X, but this is not the case. Like this is very, very much stronger than what we need to define hyperbolicity. So we will take actually a special kind of holomorphic maps, which are the ones that we call that holomorphic maps with sub-exponential growth. So it's something
So
that,
sorry, Abdelouahab.
yeah,
Could you
yeah.
come back to the previous slide? I can't understand this theorem. So
Which term?
is it really an equivalence in this theorem of Brody?
Yeah. In the compact case, it's an equivalence. Yeah, he shows that
Okay.
actually.
So
Yeah.
could you remember what is the Brody lemma? Because I forget.
Yeah, the Brody lemma is actually, thanks for the question, because I was going to mention it anyway, because the Brody lemma is some kind of reparameterization. Like, okay, so you have a holomorphic map, so we have some kind of velocity at some point, let's say at the point 0. Okay, so and what the Brody lemma says is that we can form from any holomorphic map, we can like deform this holomorphic map to like in a way such that we control the velocity of this new holomorphic map through our like on the whole disk. Okay,
Okay. Okay.
and yeah, and and it doesn't exceed the initial velocity that we fixed at 0. So, in particular, what this means is that in the complex, and this is one of the reasons why we do not take out all the holomorphic maps from Cn minus 1 to X in higher dimensions to define hyperbolicity. We take just those of sub-exponential growth, exactly because of the broad element in dimension 1. Because in dimension 1, it's actually having any holomorphic non-constant holomorphic map is actually equivalent to having holomorphic map with such like a constraint, like with controlled velocity. So it implies in particular that we have a finite order volume growth, okay, with respect to
Okay.
this holomorphic map, which is not the case in higher dimensions. So this is why we need this condition of sub-exponential growth, okay? And the thing is that, okay, like what we call really sub-exponential growth is the second condition. The first condition is actually uh,
Hello? Yeah, thanks. I understand now.
Abdelouahab,
So
maybe.
thanks, Abdelouahab, for the question. So yeah.
Yeah, actually, thank you. So actually, uh, again, this, I don't know why this problem is keep to. Okay.
Since
Uh,
another question there, can I ask another question about the same
yeah,
theorem?
sure,
Yeah.
sure.
If you can come back to the theorem. So here, just about the statement, complex line, you mean a line like degree one, like line, right? Like you don't mean, for example, quadric or something.
No. Like holomorphic map from C to X. No,
No, I mean
non-constant.
complex line. What is the definition of is quadric in P2 for you? Is it complex line or not? Like, for example, because it's by holomorphic to.
Yeah. By complex line is what I mean is just like simply a non-constant holomorphic map from C to X.
Okay.
Or let's say complex curve if you want.
Okay.
Okay.
Uh,
Uh,
yeah. Okay.
is clear?
Yeah. Sure. Thanks.
Okay, thank you. Okay, so as the first condition, we would like to take it out because actually it prevents us from showing that Pn is actually not divisorially hyperbolic in this sense. So, and this is very like this is very bad for this notion. Okay, uh, but until now, like we can't do much with this without this condition actually. And yeah, so what I call divisory, what we call divisory hyperbolic. So this notion was introduced by my supervisor, Dan Popovici, and one of his students. So they define divisorial hyperboles, a manifold to be divisorially hyperbolic if there is no such map, like with sub-exponential growth. Okay. So this is from a geometric point of view. As I said, okay, I defined this I mentioned the definition in the dimension n-1, but one can do it like with any homomorphic map from CK to X, okay? But you will see what is the purpose behind defining this from like Cn-1. Okay, so another way to define hyperbolicity, as I said, keep in your mind that the unit disk model, okay? So, or hyper like the upper half plane. Uh, it has this property on like volume growth of domains. So on like to define on hyperbolic spaces, like we can see this property of having uh, there is some kind of isoperimetric linear inequality or estimate or on volume growth with respect to the like the area of the boundaries. So and this is this is a notion which was defined, I guess, first by Sullivan in 76. So what he calls not closed at infinity or open at infinity. So it is satisfied if one of the following equivalent properties. So he proves the equivalence in the same article, or at least like he indicates that they are equivalent. So the first property is saying that the following linear isoperimetric inequality holds, that you have a control on the volumes of open bounded domains in your manifold with respect to the boundary. Of course, as you can see here, like the non-compact assumption is very important. Okay, so as you may know, like for complex geometries, non-compact compact is like means closed somehow, like no boundary. Okay, and so obviously this is not satisfied in the compact case. So a manifold with like which is open at infinity with this definition cannot be compact. And the interesting part of this definition is that this property is equivalent to having a like with respect to the same metric with which we compute the volumes, of course. The volume form of M defined by this Riemannian metric is actually the differential of a bounded form. Okay, so here is like a differential point of view to define hyperbolicity, and with this way one can like take this to work in the complex because as we know in the complex setting there are many different metric structures. Like complex geometry is rich of those. So, and one can use like these special metrics to define volume forms, and we seek for this volume form to satisfy this property. And the first, I guess, to have noticed this was Gromov. Through defining this property of what he calls detailed aboundedness. So let's take a compact manifold and take its universal cover. So we can do this with the Kähler property. So we know that in general, if you have a Hermitian metric on your manifold, you have the dimension n. So you take to the power n. It defines a volume form. Okay. And for instance, Gromov defined this in the Kähler case. So X is a Kähler hyperbolic if it admits a Kähler metric, which is actually detailed abounded. So which means that it's not only exact. So you take the Kähler metric, you pull it back to the universal cover. It's exact and has a bounded primitive form. Okay, so this is what he calls Kähler hyperbolicity, and with the simple argument, like if you raise this to the power of n, you can see that actually it is open at infinity. Okay, in the previous definition. So this is also a way like to define hyperbolicity with respect to metrics. Of course, there are some nice and quite interesting examples of these. Of course, they include like negatively curved ones and even like homotopic to these. So compact Kähler manifolds, homotopic to negatively curved Riemannian manifolds. So what Gromov mentions in his article is just like the case where they are actually negatively curved, but or even he mentions this case, but without a proof. Like it was just some kind of expectation until Chen and Yang in 2018 proved this result. And another type of examples that if we guarantee that X is scalar and the universal cover is or between parentheses by Holomorphic 2 a bounded symmetric domain in C to the dimension of X. This is also Kähler hyperbolic. So why do we assume that X is Kähler? Because actually we can have this case, but without X being Kähler, and this case is when what we call like X to be LCK or locally conformally Kähler. Like it can have a universal cover. And maybe just to mention here, maybe that one of my goals is try to generalize this definition to the LCK case, actually, because one can see that actually the work is like everything is done on the universal cover. So the most important part is there. So like we don't really use that much that the base space is actually Kähler, except in deformation results that we'll be speaking about. Okay. And Demailly pointed out to Gromov that actually also hyperconvex bounded domains are Kähler hyperbolic. Okay, so there is a quite interesting array of examples in this category of hyperbolic manifolds. This type of hyperbolicity also enjoys some kind of nice properties in terms of submanifolds and also Cartesian products of Kähler hyperbolic manifolds. So they are still Kähler hyperbolic. So it has a quite good array of examples, and I will mention later that actually it is Kobayashi hyperbolic. But before that, there were like so let's just accept this for now that they are actually Kobayashi hyperbolic. And like with this notion, Gromov proved like, or there have been that Gromov introduced. There have been several interesting results answering some questions asked by Kobayashi and others. Like for instance, Kobayashi asked about the Kobayashi hyperbolicity. That okay, does Kobayashi like hyperbolicity means that you have a quite large, in some sense, fundamental group. And this class of Kobayashi hyperbolic manifolds that are Kähler hyperbolic manifolds have this property, but in general, it is proved that it's not true because we have a counterexample that is even simply connected, actually, like that are like just complete some complete intersections. Okay, they are actually Kobayashi hyperbolic, but also simply connected. So it's not really a fundamental group property in the Kobayashi hyperbolic case, but for Kähler hyperbolic manifolds, they have this large fundamental group property. Another property is so it answers somehow a question, partially a question asked by Green and Griffiths and Lang. It's conjectured until now that actually when a manifold is Kobayashi hyperbolic, then it is actually of general type, and also its manifolds are of general type. And this is a conjecture, but which has been answered positively in the Kähler hyperbolic case. So of course, it's just enough to show that X is of general type, meaning that Kx is like the canonical bundle is big. Okay. And it shows also that they are actually Kähler-Einstein, and this is in a separate article also by Chen and Yang. And the general type part was proved by Gromov in the article where he defines Gromov Kähler hyperbolicity. And the property still true for submanifolds because they are, as I mentioned, they are also Kähler hyperbolic. Okay, and there is also still this conjecture. Okay, maybe I didn't mention here is actually that even Kähler hyperbolic has ample canonical bundle, and which is also been conjectured for the Kobayashi hyperbolic case. It's a conjecture that Kähler or projective Kobayashi hyperbolic manifolds have ample canonical bundle, but it's not proved, and it's proved partially for the Kähler hyperbolic case, and on Kähler hyperbolic manifolds, we have this kind of very interesting property on the universal cover. So these are like the L2 cohomology groups, or like harmonic spaces in degrees P are all zero except in the middle dimension, which is actually have plus infinity dimension. And using this property, Gromov proves that we have this property, which answers partially also a conjecture by Hopf and Chern, which conjectures that a Riemannian manifold with which is negatively curved actually satisfy this. Okay, so at least it is answered in the Kähler case because Kähler manifolds that are negatively curved are actually included in this category of Kähler hyperbolic manifolds. Okay, so this category of manifolds is very interesting. It answers like quite interesting questions, and what one can do is try to generalize this definition to even to the non Kähler setting. So let us recall some definitions of special non-Kähler metrics. So what we call a Hermitian metric is SKT or Plary-Crows if it satisfies the d bar omega is 0. Semi-Kähler or balanced if d of omega n minus 1 is 0. And this notion introduced by Pogovici also, which is called strong LIGO du champ, which is if the partial of omega n minus 1 is d bar exact. Okay, so the SKT property looks somehow like the Kähler one, but instead of D closedness, it's DD bar closedness. So one can see somehow how to generalize this. The balanced case also one can see how to generalize Kähler hyperbolicity to balanced hyperbolicity, just like to take this property instead of the degree 1 to degree n minus 1. But for the strongly Gaussian hyperbolicity, like with this definition, it's some kind of difficult to see how to generalize the definition. So this is why I will use here this remark. So we have this following equivalence for a metric to be strongly Gaussian if and only if there exists a real declosed smooth to n minus 2 form, which has like it's by degree n minus 1 n minus 1 component is actually positive. Okay, and actually this one defines the strongly Gaussian metric, because there is this lemma by Michelson which says that like the n minus 1th root of a positive form, n minus 1 n minus form is actually a metric. Okay. So this way one can generalize the definition of Kähler hyperbolicity to the non-Kähler context. Okay, so as you may expect, a balanced hyperbolic, it means that if we lift to the universal cover, it is detailed about omega n minus 1, not omega, is detailed abounded. And for SKT, what goes with it is not the detailed aboundedness, but the d plus d bar, which means that when you take it to the universal cover, it can be written as d alpha plus d bar beta with alpha beta bounded. Okay. And for strongly Gaussian, I will use the second definition with the remark, like in terms of the 2n minus 2 form. Okay, I just say that, okay, that your metric is strongly Gaussian hyperbolic. If it's power n minus 1, it's actually the n minus 1 n minus component, as I mentioned, of this 2n minus 2 form, which I impose to be detailed abounded. And this way one can define hyperbolicity for the strongly Gaussian hyperbolic case. So how all these notions like interact? They interact actually in the following manner. So let's say that we can separate in this like this diagram as like metric notions and like geometric notions. And the most important thing that one can one may keep from this diagram is that why the importance of metric properties is that to find like to prove that a manifold is not Kobayashi hyperbolic, for instance, it's easy. Like you have to just find one complex curve in this manifold. But to give examples, like to show that a manifold does not have any complex curve except constant ones, this is very difficult. And this is where the metric part is important, because it provides us with examples. Okay, and as you can see, like Kähler hyperbolicity and SKT hyperbolicity are properties in degree 1. They imply Kobayashi hyperbolicity. And the implication that we have in terms of metrics are also preserved. For instance, we know that Kähler implies SKT, so also in terms of hyperbolicity. Kähler implies balanced, Kähler implies strongly Gaussian. So this still isn't true in terms of hyperbolicity. And these two, like the strongly Gaussian hyperbolic and the balanced hyperbolic properties, actually they imply the divisorial hyperbolic case in by degree n minus 1 and in degree n minus 1, and this is why I defined the thing like holomorphic. We've taken out holomorphic maps from Cn minus 1 because we have examples through this balanced hyperbolic manifolds. And okay. I think I took too much time for the first part, so I will let you with this let's say like taste of proof of the fact that Kähler hyperbolic is Kobayashi hyperbolic. So it just proved by contradiction. and you lift, like you have a holomorphic non-constant map, so it defines, as I said, the pullback defines a metric. You lift it to the universal cover, and you have this following property. And you show that actually you have this linear isoperimetric of the area of the disk in terms of the length of the perimeter of the sphere. And thanks to the Gronwell lemma, you can show that this inequality implies that the volume growth of with respect to the pullback of omega of the disks is actually more than exponential, which is a contradiction. Okay, because actually I could have supposed that f is of finite order, as I said, by Brody's parameterization lemma. And like the other proofs goes like when you want to show that the metric hyperbolicity property implies a geometric hyperbolicity property, it generally goes this way. Okay. So this was my first part.